Go integer data types. Question: what are the main categories of integer types in Go, and why do they matter? Answer: Go has two main categories of integer types. The first category is architecture-dependent integers, like int, uint, and uintptr. Their size depends on the system, for example, 32-bit or 64-bit. The second category is architecture-independent integers, like int8, int16, int32, int64, and their unsigned versions. These always have the same size on every system. This matters because fixed-size integers are safer when you care about portability, data formats, or network protocols, while int and uint are usually easier and faster for normal application code. Question: what is the difference between a type alias and distinct types in Go? Answer: in Go, some types are aliases, which means they are exactly the same type. For example, byte is the same as uint8, and rune is the same as int32. Because they are the same type, you can compare them directly without any conversion. Other types are distinct, even if they look similar. For example, int and int64 are different types. You cannot compare them directly, and the code will not compile. You must convert one type to the other first. This rule helps Go be strict about types and prevents bugs caused by mixing different integer sizes. Key point: even on a 64-bit machine where int is 64 bits wide, int and int64 are different types. You must explicitly convert. Question: what are the zero values for integer types in Go, and what type does Go choose for a short integer declaration? Answer: in Go, when you declare an integer variable without giving it a value, Go automatically sets it to its zero value. For all integer types like int, int64, uint, byte, and rune, the zero value is 0. This means you can safely use these variables without manually initializing. Also, when you use a short declaration like x equals 42, Go infers the type as int, not int64. Untyped integer constants become type int by default unless you force another type.
Question: how can you write integer numbers in different bases in Go? Answer:
in Go, you can write integer numbers in different bases. For example, you can write numbers in decimal, like 42. Octal numbers can be written with a leading 0, like 052, which became clearer and recommended in Go 1.13. Hexadecimal numbers use 0x, for example, 0x2a. Binary numbers were added in Go 1.13. You can also use underscores inside numbers to make them easier to read. All these forms represent the same values if the digits match, but they help make code clearer and less error-prone. Underscore rules cannot be at the beginning or end of a literal, cannot be adjacent to another underscore, must be between digits or after a base prefix.
Question: what is an untyped constant in Go, and why is it important? An untyped constant in Go is a constant that does not have a fixed type until it is used in a specific context. It can have very large values because it uses arbitrary precision at compile time. For example, you can write const big equals 1 shifted left by 200 without an overflow error. However, you cannot assign this large value to a variable of a type like int64 if it does not fit. An untyped constant takes the type of the variable when you assign it, as long as the value fits in that type. For example, const c equals 42 can be assigned to int8, int64, or uint16 because 42 fits in all of them. If the value does not fit, like assigning 200 to int8, the code will give a compile error. The default type of an untyped integer constant is int when it is used in a variable declaration.
Question: does Go automatically convert one integer type to another, and what problems can happen when converting types? Answer: no, Go does not automatically convert between integer types. You must write the conversion yourself.
For example, you can convert int32 to int64, and this is usually safe because the larger type can store all values of the smaller type. But if you convert from a larger type to a smaller type, like int32 to int16, you may lose data. The number can change to a wrong value without any error message. Also, when you convert between signed and unsigned types, the value can change in an unexpected way. For example, if you convert -1 from int8 to uint8, the result becomes 255. So type conversion in Go must be done carefully to avoid silent data loss or unexpected results.
Question: what are math package constants like min.int8 and max.int8 used for in Go? In Go, the math package provides constants that show the minimum and maximum values for different integer types. For example, min.int8 and max.int8 show the smallest and largest numbers that an int8 type can store. The same idea applies to int16, int32, and int64. For unsigned integers like uint8, the minimum value is always 0, and the package gives the maximum value, such as max uint8. Newer versions of Go also include min.int and max.int for the default int type. These constants help developers understand the limits of each number type and avoid overflow errors.
Question: how do arithmetic operations work in Go, especially with division and negative numbers? In Go, you can use plus for addition, minus for subtraction, star for multiplication, slash for division, and percent for remainder. When you divide two integers, Go does integer division. This means it removes the decimal part. For example, 17 divided by 5 is 3, not 3.4. With negative numbers, division always moves towards 0. For example, minus 17 divided by 5 is minus 3, not minus 4. The remainder keeps the sign of the first number. For example, minus 17% 5 is minus 2. Also, increment and decrement, like x++ and x-, are statements, not expressions. You cannot use them inside another assignment, like y equals x++.
Question: what happens when an integer overflows in Go? In Go, integer overflow is silent. This means there is no error and no panic. The value simply wraps around. For example, if you use a uint8 and increase 255 by 1, it becomes 0. If you decrease 0 by 1, it becomes 255. The same happens with signed integers. If an int8 value is 127 and you add 1, it becomes -128. If it is -128 and you subtract 1, it becomes 127. Go also catches overflow at compile time when you write a constant that is too large for the type. But at runtime, overflow is not caught and the value just wraps around. Question: why do these helper functions check for overflow before doing math with int64 numbers in Go? These helper functions are used to make arithmetic safer. In Go, when an int64 number overflows, it does not give an error and the value just wraps around, which can cause serious bugs. The add int64 function checks the limits of int64 before adding two numbers. If the result would be bigger than the maximum int64 or smaller than the minimum int64, it returns an overflow error instead of a wrong number. The mul int64 function checks for overflow by multiplying first and then verifying the result by dividing it back. If the division does not match, it means an overflow happened. This way, the program can detect overflow early and handle it safely instead of silently producing incorrect results.
Question: how can you safely detect overflow or underflow when doing low-level integer math? Answer: Go 1.22 adds add, sub, and mul functions in the bits package that return extra information about overflow. For example, add64 returns the sum and a carry value. If the carry is 1, it means the addition overflowed. Sub64 returns the result and a borrow value, which tells you an underflow happened. Mul64 returns two values, the high and low parts of the result, so you can see if the multiplication exceeded 64 bits. These functions are useful in systems code, cryptography, and performance-critical code, where you must detect overflow instead of letting values wrap silently. Question: What are bitwise operations in Go, and why are they useful? Bitwise operations work directly on bits of numbers. In Go, you can use AND to keep only bits that are 1 in both numbers, OR to keep bits that are 1 in either number, and XOR to keep bits that are different. NOT flips all bits, turning 1 into 0 and 0 into 1. And NOT is used to clear specific bits. Shift operations move bits left or right. Left shift makes a number bigger by moving bits to the left. Right shift makes a number smaller by moving bits to the right. For signed numbers, right shift keeps the sign bit, so negative numbers stay negative. For unsigned numbers, right shift fills with zeros. These operations are useful for low-level tasks like flags, masks, and performance-critical code.
Question: what does the Go operator in bitclear do, and when would you use it? The bitclear operator in Go means AND NOT. It clears bits in one value using another value as a mask. First, Go flips the bits of the mask. Then it applies AND. Any bit that is 1 in the mask will be cleared in the original value. For example, if flags has all bits set and the mask has bits 2 and 3 set, using AND NOT with the mask will turn off only bits 2 and 3 and keep the rest unchanged. This is useful when you want to remove specific flags or options without touching other bits. Question: in Go, what happens with negative shift values? Since Go 1.13, the shift count can be a signed integer, like int, not only an unsigned type. This means you can write code like 1 shifted left by an int variable, and it works. However, if the shift value is negative, it is not allowed. A constant negative shift causes a compile time error, and a variable that becomes negative at runtime causes a runtime panic. So shift counts can be signed, but they must never be negative.
Question: how can bitwise operations in Go help with common tasks, like checking even numbers, powers of 2, and setting or clearing bits? Bitwise operations in Go let you work directly with bits. For example, you can check if a number is even by testing the last bit with in and 1. If the result is 0, the number is even. To check if a number is a power of 2, you can use x and x minus 1. For positive numbers, the result is 0 only for powers of 2. You can set a specific bit by shifting 1 to the desired position and using OR, clear a bit using AND NOT, and toggle a bit using XOR. Shifting bits also helps with multiplying or dividing by powers of 2, like shifting left to multiply or right to divide. These tricks are common in low-level code, flag handling, and performance-critical logic. What is the bits package in Go used for, and why is it useful? The math/bits package in Go is used for low-level bit operations on integers. It helps you count how many bits are set to 1, find the length of a number in bits, and count leading or trailing zeros. You can also rotate bits left or right, reverse the order of bits or bytes, and do full-width division with functions like div64. This package is useful for performance-critical code, working with binary data, cryptography, compression, and systems programming, where direct control over bits is important. Question: how can I print an integer in different formats in Go, like binary or hex, and control its width and padding? In Go, we use Printf with format verbs to print integers in different ways. %d prints a number in decimal, %b prints binary, %o prints octal, and %x or x prints hexadecimal in lower or uppercase. Using %hash with these adds prefixes like 0b or 0ff. %c prints the number as a character, and %u prints its Unicode. %v prints the default value, and %t prints the type. Some formats are only for floats, so using %e with an integer gives an error. You can also control width and padding. For example, a number can be right-aligned, left-aligned, or padded with zeros by adding a width like 10 or using 0. You can force showing the sign with plus, or reserve space for it with a space. This is useful when you want clean and aligned output. Question: how can we convert between strings and integers in Go? In Go, we use the strconv package to convert between strings and integers. To convert a string to an int, we can use atie for simple base 10 numbers. If we need more control, we use parseInt or parseuint, where we can choose the base, like 2 for binary, 8 for octal, 10 for decimal, or 16 for hex. The bit size parameter checks the number range. for example, int8 or int64, and gives an error if the value is too large. To convert an integer to a string, we can use iota for base 10. For different bases, we use format int or format uint. We can also use sprintf, but it is slower and more flexible.
Question: what does unsafe.Sizeof show in Go, and why does struct field order matter? Unsafe.Sizeof shows how many bytes a variable uses in memory. For example, int8 uses 1 byte, int16 uses 2 bytes, int32 uses 4 bytes, and int64 uses 8 bytes. On a 64-bit system, int and uintptr usually use 8 bytes. Struct field order is important because of padding and alignment. The compiler may add extra empty bytes to align data in memory. If fields are not ordered well, the struct can use more memory than needed. For example, a badly ordered struct can use 24 bytes, but a well-ordered one with the same fields can use only 16 bytes. Proper field order helps reduce memory usage. To minimize memory waste from padding, order fields by size in descending order. Question: what should we know about integer-related type conversions in Go? In Go, you cannot mix different integer types without converting them. For example, you cannot add an int and an int32 directly. You must convert one type to the other first. Type conversion in Go is explicit, which means you must clearly write the target type, like int32. Go does not perform automatic integer conversions for you. Also, when converting between different integer sizes, such as from int64 to int8, you can lose data if the value is too large. So you should always be careful about overflow and data loss when converting integer types. Question: how do comparison operators work in Go, and what should you know about comparing different types? In Go, comparison operators are used to compare two values and return true or false. The main operators are equal to, not equal to, less than, greater than, less than or equal to, and greater than or equal to. For example, if A is 10 and B is 20, then A is less than B, so A less than B is true. If you try to compare two variables with different integer types, like int32 and int64, Go will give a compile error. You must convert one type to match the other before comparing them. However, you can compare a typed variable with an untyped constant, like the number 10, because Go automatically adjusts the constant to the correct type. Question: what is the difference between byte and rune in Go? In Go, byte is used to store raw data, like ASCII characters or binary data. A byte is just one small number between 0 and 255. A rune is used to store a Unicode character. A rune can represent characters from many languages, not only English. When you use len on a string in Go, it returns the number of bytes, not the number of characters. This is important because some characters, like Chinese characters or emojis, use more than 1 byte, so the byte length can be bigger than the real number of characters.
Question: what is big.Int in Go, and why should we use it? Big.Int is a type in the math/big package that lets you work with very large integers. Normal integer types like int or int64 have size limits, but big.Int can store numbers as large as your memory allows. You can create a big.Int from a normal number, from a string in base 10, or even from other bases like base 16. Arithmetic operations such as add, mul, div mod, and x are done using methods, and these methods change the value of the receiver and return it. Big.Int also supports modular exponentiation, which is useful in cryptography. Question: what is the difference between int64 and big.Int in Go? The main difference between int64 and big.Int is size and performance. An int64 has a maximum value of 2 to the power of 63 minus 1, so it has a fixed limit. It uses 8 bytes of memory and is very fast because it uses native CPU operations. It is stored on the stack and does not create garbage collection pressure. On the other hand, big.Int can store very large numbers without a fixed limit.
Question: how do generics work with integer types in Go? In Go 1.18 and later, you can use generics to write functions that work with different integer types. For example, You can write a sum function that accepts a slice of any integer type and returns the total. This works by using a type constraint like constraints.integer or a custom interface that lists allowed types. You can also create your own constraints, such as signed and unsigned, and combine them into an integer constraint. The tilde symbol before a type, like in int64, means the function also accepts custom types that have int64 as their underlying type. For example, if you define type user ID int64, you can still use it with the generic sum function. Generics let you write one reusable function for many integer types while keeping type safety. Question: what is cmp.Ordered in Go 1.21 and why is it useful? In Go 1.21, the standard library has a package called cmp. It provides a constraint named ordered. The cmp.Ordered constraint is used with generics and allows a type parameter to be any type that supports comparison operators like less than or greater than. For example, in a generic men function, we can write men with a type parameter t that must satisfy ordered. This means t can be int, float, string, or any other order type. Inside the function, we can safely use the less than operator to compare two values. This makes it easy to write reusable functions that work with many basic comparable types without repeating code.
Question: what is Endianness in Go, and how does binary encoding work? Endianness is the order in which bytes of a number are stored in memory. In Big Endian, the most significant byte comes first. For example, the number 0x01020304 is stored as 01020304. In Little Endian, the least significant byte comes first, so the same number is stored as 04030201. Go provides the encoding/binary package to write and read numbers in both Big Endian and Little Endian formats. It also supports variant encoding, which stores numbers using a variable number of bytes. This method saves space and is used in systems like protocol buffers. Go can also detect the native byte order of the system, which is Little Endian on most modern computers. Question: what are atomic integer operations in Go, and why are they useful? Atomic integer operations in Go are special functions that let many Go routines safely read and change the same integer value at the same time. They prevent race conditions without using a mutex. For example, atomic.addInt64 can increase a counter safely, and atomic.loadInt64 can read the value safely. There are also functions like store, swap, and compare and swap.
Question: what is iota in Go, and why is it useful? Iota is a special keyword in Go that is used to create a sequence of integer constants. It starts from 0 and increases by 1 for each line inside a constant block. This helps developers create simple numbered constants like 0 and 1 without writing the numbers manually. Iota is also useful for creating bit flags using bit shifting, such as 1, 2, and 4, which can be combined for permissions like read and write. It can be used to define custom types like weekdays, where each day has a number value. You can skip values, start from a different number, or use iota inside expressions. Iota makes constant definitions clean, short, and less error-prone. Question: how can a Go program find the size of int on the current platform? In Go, the size of int depends on the platform, usually 32 bits on 32-bit systems and 64 bits on 64-bit systems. This is important because it helps you write safe code that works correctly on all platforms. For example, you can calculate the maximum and minimum int values in a safe way, using bit operations instead of assuming a fixed size. Why is it usually better to use the standard int type instead of smaller types like int8 for performance in Go? You should usually use the standard int type because it matches the size of the computer's internal registers. This makes it the fastest option for most tasks. While small types like int8 might seem like they save space, they can actually slow down your program because the computer often has to add extra padding to fit them into memory correctly. Unless you are working on a specific network protocol or need to pack a huge amount of data, sticking with the regular int is the best choice for speed. Question: what type should I use for a loop counter in Go, and why? You should usually use int for a loop counter in Go. The int type matches the platform word size, so it is the fastest and most natural choice for the CPU.
Question: in Go, should I manually replace division or multiplication by powers of 2 with bit shifts for better performance? No, you do not need to do that. The Go compiler is smart and already optimizes this for you. When you divide a number by a constant power of 2, like 8, the compiler can turn it into a right shift. When you multiply by a power of 2, like 16, the compiler can turn it into a left shift. This means your normal code is already fast, and writing clear code is better than manually using shifts. Question: in Go standard library functions, which integer types are commonly used, and why does this matter? Many standard library functions expect specific integer types, so using the right type avoids errors and conversions. For example, len and cap return int, because int matches the platform word size and is efficient. Functions like make for slices and buffers also expect an int size. Many APIs, such as io.readRead, strings.count, HTTP status codes, and scanner buffer sizes, use int for counts. Time is special, because time.duration is in64 and stores nanoseconds.
Question: why can large integers become wrong when decoding JSON in Go, and how can we fix this problem? JSON numbers are decoded using floating point rules, and numbers larger than 2 to the power of 53 can lose precision. This means very large integers may become truncated or incorrect when unmarshaled into int64. One simple solution is to send the large number as a string in JSON and store it in a string field, which keeps the value exact. Question: why is uintpy dangerous for pointer arithmetic in Go, and how should it be used safely? uintpy is an integer type that can hold a memory address, but it is not a real pointer. The Go garbage collector does not track uintpy values, so if you store a uintpy and use it later, the garbage collector might move the object and the address becomes invalid. This can cause crashes or wrong data. Pointer arithmetic with uintpy is only safe when it is done in a single expression, converting from a pointer to uintpy and back immediately. You should never save a uintpy in a variable for later use. The safe pattern is to do the calculation and conversion back to unsafe pointer right away, so the garbage collector can still see the original pointer during the operation.
Question: what does this Bloom filter code do, and how do set and test work using bits? This code implements a very simple Bloom filter using bit manipulation. The Bloom filter stores data as bits inside a slice of uint64 values. Each uint64 holds 64 bits, so many Boolean flags can be stored in a small amount of memory. The new Bloom function creates the filter and allocates enough uint64 values to cover the requested size and bits. The set function turns on a bit at a given position by finding the correct uint64 using pos divided by 64, and then setting the bit using a left shift. Question: what is a bit set in Go, and how do set and has work? A bit set is a compact way to store many true or false values using bits instead of separate Booleans. This implementation stores bits inside a slice of uint64 values, where each uint64 holds 64 bits. When you create a new bit set with a size n, it allocates enough uint64 words to cover n bits. The set function turns a bit on by finding the correct word using I divided by 64, and then setting the correct bit inside that word using I modulo 64. The has function checks if a bit is on by testing the same position and returning true if that bit is not 0. This approach is memory efficient and very fast for checking, setting, clearing, or toggling flags.
Question: how can we convert an IPv4 address to a number and then convert it back in Go, and why is this useful? You can convert an IPv4 address into a 32-bit number by taking each of the 4 parts of the IP and shifting them into one uint32 value. This makes the IP easy to store, compare, or sort as a number. First, the IP is converted to IPv4 form using 2.4. Then, each byte is shifted and combined into one number. To convert it back, you reverse the process by shifting the number and reading each byte to build the IP again. This way, an IP like 192.168.1.100 can become a single number and later return to the same IP without losing information. Question: how can you check an integer type at runtime in Go?
In Go, you can check an integer type at runtime by using an empty interface and a type switch. A type switch lets you test the real type stored in an interface value, such as int, int8, int32, or uint8. This is useful when you do not know the exact type in advance. Question: what is the best way to know the size of int in Go when working with different CPU architectures? In Go, the int type can be 32 bits or 64 bits, depending on the architecture. One old way is to use build tags and create different files for 32-bit and 64-bit systems, but this makes the code harder to maintain. A better and simpler way is to detect it at runtime using strconv.int size. This value is set by the compiler and tells you directly whether int is 32 or 64 bits, so it works well for cross-compilation and keeps your code clean. Complete integer types table. Pros-cons table. When to use which type. Quick reference: choosing the right integer type.